In the previous video, we discussed a few aspects of GPU architecture, where we looked into concepts like CUDA cores, warps, streaming multiprocessors, and their functioning with an example of a CUDA kernel launch. Now, as part of this video, we will look into the memory hierarchy of the GPU. Like a CPU, the GPU relies on a memory hierarchy, from RAM via cache levels, to ensure that its processing engines are supplied with the data they need to do useful work. And just like the CPU cores, the streaming multiprocessors in a GPU finally require the data to be in registers to be available for computations by CUDA cores. This means registers feed data directly into the CUDA cores. As shown in the diagram, each streaming multiprocessor in a GPU has around 64,000 registers in its register file. Hence, compared to a CPU core, a streaming multiprocessor in a GPU has many more registers. L1 cache refers to the usual on-chip storage location that provides fast access to recently read or written data to the global memory. Additionally, L1 serves as the overflow region when the amount of active data exceeds what a streaming multiprocessor's register file can hold, a condition which is termed register spilling. Shared memory is a memory area that physically resides in the same memory as the L1 cache, but differs from L1 in that all its data may be accessed by any thread in a thread block. This allows threads to communicate and share data with each other. In CUDA kernel code, a variable in shared memory can be declared using a shared keyword, as shown here. This will create a variable named S in the GPU's shared memory, which any thread of the same thread block can use. Arrows in the diagram show how the layers of memory are linked together. Depending on where the data starts, they may have to hop through several layers of cache to enter the registers of a streaming multiprocessor and become accessible to the CUDA cores. Global memory is by far the most significant layer and the furthest from the streaming multiprocessors. L2 cache is an additional on-chip cache for retaining copies of the data that travel back and forth between the streaming multiprocessors and main memory. Like the L1 cache, the L2 cache is intended to speed up data access. However, unlike the L1 cache, there is just one L2 that is shared by all the streaming multiprocessors. Notice that the L2 cache mediates data transfers onto and off of the external devices like the CPU using NVLink or PCIe bus. Also, all the data traffic flows through the L2 cache, as all streaming multiprocessors are connected through the same L2 cache. Hence, the L2 cache is a proxy for global memory. All global memory accesses go through the L2 cache. The oldest data in the L2 cache will be written out to global memory when it needs to make space for new data. Global memory represents the bulk of the GPU's main memory, equivalent to RAM in a CPU-based processor. Texture and constant memory are regions of main memory that are treated as read-only by the GPU. Texture memory is fast read-only memory that is optimized for two-dimensional spatial access, whereas constant memory is specific to each streaming multiprocessor and is 64 kilobytes in size. Within the CUDA application, it can be created and accessed using the constant keyword, as shown here. Here, in CUDA code, array A is declared as a constant, which can then be used for read operation. With this, we conclude the memory hierarchy for GPUs. I hope you find this helpful. Thanks for watching.